Welcome to this acoustic webinar, which is the third webinar on acoustics of this year. And the topic is about acoustic simulation for the aeronautic industry. So let's take a look at the agenda of today. So first, we will give a very brief review on the main contributors of aircraft noise. And then we will see take a look at the Actran modules, which is also a review of the modules, and see how these modules could be applied on to solve different aspects of aircraft noise. And we will address the aircraft exterior noise and the interior noise, with the sources being from the engine or the APU, or from the airframe noise. For the interior noise, we have contributions from the turbulent boundary layer, which is causing noise in the cabin or in the cockpit, and also noise from the environmental control system, etc. And after the PPT presentation, I will give a short demo on a vibro-acoustic model of noise transmission from outside the fuselage into the fuselage and into the cabin. And then this demo will be followed by a Q&A session. So first, a review of all the aircraft noise contributors on which we FFT have worked on with Actran. So we could divide all the contributions into interior noise and exterior noise, or radiated noise. Now let's, if we take a look at the overall interior noise level, we know that this overall noise level is composed by many different sources in the aircraft. Some sources are located inside the aircraft itself. Some are generated by devices outside the cabin. Now, for sources that are located in the aircraft, we have noise sources from, for example, the environment control system, the avionics electronic system, or some hydraulic system noise, etc. While these interior noises are sources to the perceived interior noise by the passengers, while the main contribution to the interior noise are actually coming from the exterior, mainly from the engine. It could be a turbofan engine, or a propeller engine, or even a counter-rotating open rotor, which is a new concept of engine. And another part of the external noise sources is coming from the turbulent boundary layer created by the viscosity of the air while the aircraft is cruising. And these sources will be transmitted into the aircraft by different paths. For example, by the airborne path, or by the structure-borne path, meaning that the vibration of the engine will cause vibration of the wing, that will cause vibration through the fuselage, and this vibration was transmitted into the interior cabin and create noise. And turbulent boundary layer will be transmitted through, obviously, the structure, the fuselage, but also through the windows, which are actually a weak point of acoustic transmission in terms of acoustic insulation. And for radiated noise or external noise, we are talking about also engine noise. During landing or takeoff phases, this is essentially related to the certification. So at certification of engine and aircraft, there will be 3 points defined to measure the emitted noise of engine. And APU, so auxiliary power unit noise, the air intake of APU and air exhaust of APU will also generate noises. And in general, airframe noise, which are of broadband nature, caused by, for example, landing gear or the high lift devices like the slab and flat on the aircraft wings. So as I said, all these noise sources and their transmission paths have been analyzed using Actran. So today I will pick some major noise sources and transmission paths and discuss how these problems could be addressed by acoustic simulation. So on this page, we will review briefly the Actran modules. So interestingly, Actran has many modules, and all these modules are actually applied in the aeronautical industry to solve different type of noise sources that we have just seen. So the basic module of Actran is called acoustics module. It solves acoustic propagation, like this one in the middle, in free field, or acoustic propagation in duct systems, or acoustic resonance in cavity problems. We can also apply some acoustic treatment using equivalent impedance boundary conditions in this Actran acoustics module. And this module also features acoustic propagation in flow, so we could solve convected acoustics also in the basic module. Now, as the physics become more complex, we will need more advanced modules to address the challenges. So on the left part, we have the vibro-acoustic branch. So the Actran vibro-acoustics module solves a strongly coupled structure and fluid problem. So the fluid can be internal fluid in the structure or external fluid outside the structure. And the structure can be coupled on both sides towards both fluid. And we can also introduce acoustic absorbing material like the foams or glass wools in the vibro-acoustic module. This module, Actran for Nacelle, is a module that couples the modal representation of the structure from Nacelle to the physical representation of the acoustic cavity or of the acoustic material in Actran. So it combines the strengths of both software, modal representation for large structure in Actran, and physical representation for absorbing material in Actran. And in the middle, we have Actran aero-acoustics. It solves general broadband flow-induced noise or fan noise containing both tonal signals and broadband signals. To solve aero-acoustic problems, we need to couple Actran with a commercial CFD code. So CFD code will solve the turbulent flow, and Actran read the turbulent flow, generate noise sources using acoustic analogy, and then does the acoustic propagation. Then the last two modules were designed specifically for aircraft engine problems. So Actran TM means turbo machinery. It is very well suited for intake problems of aircraft engines or APUs. And the Actran DGM is the module that it's the only module that doesn't work on additional finite element method. So the method is called a discrete Galenkin method, so Actran DGM, and it was developed specifically for engine exhaust acoustic propagation. Now, apart from DGM, all the other modules are in the finite element approach, which means there's no technology barrier between different modules for them to communicate. So a aero-acoustic problem can be perfectly connected to the vibro-acoustic problem to solve a bigger problem with more physics involved. Okay, now let's apply all these Actran modules and these technologies on different aspects of aircraft noise. So for exterior noise, we will look at three main forces. The noise from the main engine, and the noise from auxiliary power unit or APU, and the noise related to the general turbulence flow, the airframe noise by the landing gear or by the high lift devices. So first, the Actran technology to solve turbo engine noise. So this picture shows a structure of a turbo engine, and the noises related to the turbo engine are mainly the intake noise, bypass noise, and the exhaust noise by the turbine. Let's take a look at the characteristics of all these noise sources. The acoustic propagation in the intake part is basically acoustic propagation in the potential flow. So the background flow at the intake is a complex one. However, it is a potential flow, or it is close to a protection flow, meaning there's no rotation term in the flow. And the acoustic propagation from the fan towards outside can be attenuated by the acoustic liners that are designed on the nacelle. So the main topic here is the nacelle design and the liner design for the intake acoustics. And the propagation in exhaust is a little different from the propagation in intake in nature, in the sense that the acoustic is propagating in a rotational flow. So we will have some shear layers here at the exhaust. For example, between the bypass and the exterior air, there will be mainly a velocity shear layer. And between the turbine exhaust and the bypass exhaust, there will be a shear layer that is not only a velocity one, but also a temperature shear layer, which is more complex one. And also the acoustic propagation here can be attenuated by the liners, for example, the liners in the bypass duct. And the sources here are mainly created by the fan, by the rotating devices, either the fan or the turbine here, and they all have a very tonal behavior, meaning that the sources are mainly remarkable at the blade passing frequencies of those rotating devices. So the task of reducing noise is mainly to design the acoustic attenuation that are specifically working on these tonal frequencies. In Actran, in order to represent the noise sources, for example, in this turbofan engine created by the fan, we will plug an analytical representation of the acoustic duct. It's also called the modal duct. We will plug this modal duct to the finite element model in Actran. So the modal duct are analytical solutions of the pressure distribution on a certain cross-section of the duct. So the most basic pattern being a plane wave on the left. We have also high-order modes that will occur in the duct from their intrinsic cut-on frequencies. So more complex the mode is, higher the cut-on frequency will be, which means only at higher frequencies the complex modes will propagate from the fan towards the exterior. Now, sometimes, sorry, I didn't mention this one. So in Actran, we can plug the modal ducts of three types of geometries: the circular one, or the annular one, like this one in the real fan design, or rectangular shapes. But sometimes we will have geometries or shapes different from these ideal shapes. For example, this case on the left, we have the intake of a turbo propeller engine, and we see that this surface is a random surface. It's not an annular one or a circular one. Or sometimes we have the obstacles like pylons in the bypass or in the engine structure. Now, to represent acoustic sources created on this type of surface, we will need the numerical modal duct, which is also a pressure distribution on the duct surface, but this distribution is calculated numerically using the Actran solver. Okay, so once we have the source definition, either analytical or numerical, we'll be able to propagate these sources in the finite element mesh and design the liner impedance that will absorb these sources in order to achieve acoustic attenuation. The liners are those type of for example, the liners in the aircraft nacelle are these types of honeycomb structures that are buried beneath the surface of this this nacelle interior surface. So we'll have in the liner design, we'll have single degree freedom liners or double degree freedom liners, and so each of them will have their own specific acoustic impedance. And in Actran, we will model the liner by their impedance boundary condition. So basically, we will define this surface using an impedance boundary condition. In modeling of engine acoustics, taking the flow heterogeneity is very important because the flow heterogeneity will modify the acoustic propagation from several ways. Now, the velocity will modify the acoustic propagation and bringing a Doppler effect suppose at the engine intake, the acoustic is propagating against the flow, and at exhaust, acoustic propagate along the flow. And since the flow is anyway an important one, it will modify significantly the acoustic propagation. And also temperature gradient. As we have seen, we have temperature shear layers in the exhaust, which modifies the local speed of sound, and that will also modify significantly the acoustic propagation at the exhaust part. So taking these flow heterogeneity are important, and the way of taking them into account is through a flow mapping technique. In the flow mapping, the first step is to calculate all those aerodynamic fields, including velocity, temperature, pressure, and density, either in a commercial CFD code or in Actran flow solver. Now, if we have a potential flow, example at the intake, we can use Actran for the calculation. Of course, we can also use a CFD solver. Now, for the exhaust flow, Actran doesn't have the capability to calculate that rotational flow. We will need a CFD solver. And then the flow calculated by the CFD will be projected on the acoustic mesh in Actran through this ICFD utility that is an embedded utility in Actran. And then the third step, the acoustic simulation will naturally take the flow heterogeneity into account. So we are counting the modification of the flow to acoustic propagation. Now some sample examples. So first, we are seeing a nacelle problem modeled in a 2D axisymmetric model. So we are modeling only this one surface, axisymmetric surface, to represent the 3D problem. We see that at the fan location, we will apply a Modal excitation, simulating the fan excitation. And then at different locations on the nacelle, we will model the absorption by, well, in Actran, we will apply admittance, which is basically the inverse of impedance. So it characterizes the absorbing capability of the liner. And acoustic propagation will be performed in the near field through finite element mesh. And for far field radiation, we will use the infinite element technology. So acoustic waves reaching this interface will not be bounced back. It will propagate without reflection to far field. So the microphone positions can be, of course, in near field, but also in far field. So this is a picture on the bottom left. This is a flow calculated by Actran. And on the right, we see a color map of acoustic propagation. Here we are looking at 4 different axisymmetric models. So on the left, we are looking at 2 models with and without liner absorption. So you can see that on the left, there's the liner absorption, and on the right, there's no liner implemented. On the right, we see the mean flow influence. On the left, there's a without mean flow, and on the right, the mean flow is modifying the acoustic propagation. So we see that the acoustic waves are compressed in a way. And in terms of directivity in far field, we see that with the liner designed, we see a drop of sound pressure level measured at a majority of the microphone positions in far field. Okay, the next example is a APU inlet modeling. The principle is very similar to the engine nacelle modeling. In this APU problem, we model the acoustic propagation from inside aircraft to through the APU inlet to the towards the exterior field, and we also apply on the inner duct, on the surface of the inner duct, an admittance boundary condition. And as acoustic propagates throughout the infinite element, we will have no reflection through this infinite element. So we can calculate a transmission loss, sound transmission loss, defined by the ratio of the incident acoustic energy and the transmitted acoustic energy. Now, so on the right bottom, we see this chart of modification of transmission loss by different admittance values that were predefined and applied in the duct. We see that without any admittance or without any liner, there's a very low transmission loss. And with different values of admittance, we see different transmission loss values. So this demonstrates the ability of Actran to for the liner design in APU inlet. Okay. The following topic is the engine exhaust noise propagation. And for this problem, we will use a different technology, namely Actran DGM. So DGM is the stands for discontinuous Galerkin method. Why we use DGM for this problem, as I explained, we have a very complex rotational flow here. So acoustic propagation through this flow will not be handled correctly using the conventional finite element method that solves the convected Helmholtz equation. So here we will solve a linearized Euler equation using DGM in time domain approach. So although we work in time domain, we can still convert the final acoustic result into frequency domain and have access to the tonal result created by the turbine. And Actran DGM is also a very scalable tool which runs extremely scalable in parallel computation, and it's very well suited for large problems. So for example, we are able to run a 3D problem involving more than 500 cubic meter problems, and to study the non-symmetrical effect by for example, the pylon or the installation effect of the engine on the aircraft wing. Okay, now the next topic is the airframe noise created by landing gear or slap and flat. So this noise is has a broadband nature, and to solve this problem, we will need to our technology is to use a hybrid CFD and acoustics simulation. Now, in this hybrid method, a first step is to run a transient CFD solution using a commercial CFD tool like Fluent, like StarCCM Plus, or any CFD tool. And we will get the final step of that CFD computation, the time step result containing the flow velocity and the flow the air density in different time steps. And Actran will read the CFD result and transform the CFD result, flow result, into acoustic sources using a acoustic analogy technique. So basically, we are using the light hill analogy or mooring analogy for high Mach number problems. And the propagation is done in Actran. So here it is a simple validation of a simplified landing gear model. It's basically a double cylinder problem. And we can see that using this technique, hybrid technique, we obtain a very good matching between the Actran result and the experiment result. Okay, now we have seen some sources and techniques for solving the exterior acoustic problems and design attenuation techniques. Now let's take a look at all the interior acoustics in the cabin or in the cockpit. So there are also multiple noise sources contributing to the cabin noise. For example, the turbulent airflow around the fuselage when the aircraft is cruising, or the duct acoustics by the environmental control systems, but also the turbo engine or the propeller noise will also travel using through an airborne or even a structure-borne path into the aircraft interior. So a major contribution to the interior noise is by the turbulent boundary layer. This is due to the air viscosity. So this turbulent boundary layer is created on the surface of the fuselage of the cockpit, and it's transmitted. It is causing the vibration of the fuselage and transmitted into the aircraft cabin. And to design attenuation, to design methods for noise attenuation, the typical method is to implement thermal acoustic material like the glass wool for turbulent boundary layer, or use some commercial liners for, well, mainly for the using the liners of this honeycomb structure, mainly for the attenuate the propeller or engine noise. Okay. Now, numerically, there are several methods to model the vibro-acoustic problem of the fuselage and the cabin cavity. The first alternative is a hybrid modal and physical approach. So in this approach, the fuselage structure will be modeled in a modal representation, which means we will run first a modal reduction in Actran on the structure. We can also run this modal reduction for the cavity, for the air cavity, but the air cavity can be modeled also in physical approach. and the acoustic material has to be modeled in physical approach because the absorbing properties of this material depends greatly on frequency, and it cannot be. And if there's a very important damping in the material, so it could not be modeled in Modal approach. So with alternative 1, we are combining Actran and Nacelle and Actran capabilities to solve the problem. Alternative 2 is to solve the problem purely in physical approach. So you will see this is our preferred way. Now, in this approach, Actran will model not only the cavity, acoustic material, but also all the fuselage, all the structure, including the skin, the window, could be a multi-layer window, all the stiffeners inside, and the floor, of course. So, as I said, there are two alternatives, but for aircraft application, when the frequency increases, the modal density of the structure will also increase, and at some moment, the benefit of modal reduction in Actran will simply disappear. So in that case, the alternative 2 is often preferred by us. Now, a problem of alternative 2 is that we have to model the structure in Actran, but this doesn't mean we have to model them from scratch. So indeed, in Actran, we have a very nice utility called Nacelle to Actran converter, or Nacelle to Actran translator. So this translator will can easily translate all the Nacelle structural properties into Actran structural properties. So suppose we have a Nacelle model of the fuselage, just by one click, it can be translated into a Actran model, and then in Actran we'll simply combine these structural properties with the internal cavity, with the foam modeling, etc. So a typical Actran vibro-acoustic model will take all this list of ingredients into account. We'll have the fuselage skin that could be made of aluminum or innovative composite material. We can model the window by the laminated window by different layers of materials. We have elastic layers and some damping layers in between. Stringered frames, those are the stiffeners, and floor, acoustic cavities, glass wool, liners, and of course in Actran we'll apply the turbulent boundary layer excitation to the exterior surface of the structure. We can output many indicators. Now, one indicator is very interesting. It's called the noise reduction index. So it describes the noise reduction by the whole vibro-acoustic system. It is defined as the ratio between the average, the square, how to say that, the mean square pressure on this exterior surface of the structure and the mean square pressure inside the cavity. So the ratio of these two terms will give us an idea of the noise reduction of that system. Okay, now next topic, environmental control system noise. So this basically comes back to the duct problem that I presented 1 month ago in another webinar dedicated to intake and exhaust systems. So I will not develop here again, but basically we are able to analyze the acoustic propagation in complex duct with bifurcation also, and couple the acoustic fluid part with the structure part to calculate sound transmission loss, but also energy balance in the system. So with a unit energy injected to the duct system, we can see a distribution of that energy into transmitted power, reflected power, or power that causes structure vibration, dissipation, and radiated power by the vibration of that structure. So by changing the shape of the duct material, or adding insulation material surrounding the duct, we can also achieve acoustic attenuation. Now, the last topic here is about optimization. So in acoustic simulation, many times we want to find the optimal acoustic treatment by, for example, porous material, or by its honeycomb-shaped liners. And there are many parameters that we can vary to reach a acoustic attenuation. So as we know that Actran is a code that can be driven by API. So API is the application programming interface. So basically, these are the session files that can be scripted in Actran. So to run a optimization project like this one in the SOFTAIR project, in which we studied design of an optimal acoustic treatment for an air conditioning plenum, we could drive an optimization chain involving many parameters by a script file, or by a let's say a commercial optimization software like for example Optimus, and this will allow us to perform a design of experiment test. Now, in particular, in this project, we use API to link Actran and Actran to generate the mesh to vary the different parameters like the porous material properties or the shape of these honeycomb parameters. And finally, we found the optimized configuration of this multi-layer acoustic treatment, and it turns out that this numerical prediction of that optimized design correlates very well the measurement of that specific design experiment. So optimization is an important task, and it can be driven by scripting and API. So later in this year, in another episode of our acoustic webinar series, there will be a dedicated session on API and scripting. So please stay tuned on the following webinars in this specific topic. So that is my presentation, PPT presentation. And very briefly, I will give you a demo on this vibro-acoustic problem. So it's the fuselage loaded by a diffuse sound field. So in this problem, we will study the fuselage, the acoustic treatment inside, and the cabin cavity So this is a complex vibro-acoustic problem, which is loaded by a diffuse sound field or by a turbulent boundary layer from the exterior surface. Now, this diffuse sound field can be applied using built-in excitation in Actran. It can also be reproduced in the reverberant chamber test. Now, a turbulent boundary layer can be applied numerically easily in Actran, but an experiment is not that easy to apply a turbulent boundary layer in a test situation. So there's clearly a added value of simulation for this type of excitation. And the output indicator is again the noise reduction calculated by Actran. So I will share all my screen. Okay, so I previously built up this model. So here I will just guide you to view all the different components, numerical component in this vibro-acoustic problem. We will not launch the model because it has been already launched, and we will do the post-processing in Actran VI as well. This is the graphical interface of Actran. It's called Actran VI, in which we will build the Actran model. So here we are building a direct frequency response analysis, meaning that all the components, the cavity, the fuselage, the acoustic treatment, they are all in physical coordinate and there's no modal reduction in it. We define a logarithmic scale of the frequencies from 10 Hertz here to 1,500 Hertz. And the different components in this model include the fuselage. Okay. Now it is made using a isotropic material, which is the aluminum material, and the window. Now this is a simplified model with some hypothetical properties. While this is for a demo purpose, while the a more realistic problem can involve multi-layer window modeled with solid shell. For example, here in this problem, we are using thin shell of the window that has a homogeneous acoustic material properties here. And the glass wool, okay, layer. It's another color. Okay. And commercial liner, we can, again, it's a simplified model. We are using a thin shell component, while it could be modeled using more realistic and complex configuration. And let's take a look at the air. Okay, So we have the cabin air, modeled using finite fluid material, and the also the air domain under the floor. Now, the floor is not modeled in this problem, so it is assumed as a rigid separation between these two air problems. While we could also model this floor using solid material. Okay, and we see that there are several interfaces and coupling surfaces between the different domains. Now, in Actran, the modeling is quite flexible. We can couple different parts that don't share the mesh into a global model using this interface technology. So we simply define the, for example, the interface here, this one, between the fuselage and the external surface of this air domain. So in this way, these two parts that are not meshed together, that are meshed independently, are now connected in this model. Okay. Now, when this model is run, we will get indicators, many of them. We post-process the result and all these indicators in PLT viewer. That is the 2D plotting tool in Actran. So here I will plot the noise reduction indicator. So first, I will get the incident mean pressure. Okay. Square pressure. The mean square pressure of the incident surface. I will apply a noise reduction indicator here and drop the mean square pressure of that incident pressure on the incident part. And for the response in the cavity, in the upper cavity, I'm looking for the cabin air here and get its mean square pressure in it and bring it to the transmitted part here. Okay. Now this curve shows the typical noise reduction curve in this vibro-acoustic problem. Now coming back to our slide, the last slide here, as we see that by varying the parameters or adding different design component, we can see that this noise reduction curve will also change. For example, from the red curve, including the aluminum skin and stringer frames, to the black curve that adds a floor modeled in the problem, we see that the change is mainly in the lower frequency range. This part is mainly driven by the mode of the structure, and as frequency increases, the problem is more driven by the mass effect, and we see that there's not much effect of the floor on the noise reduction. However, when we add the glass wool, acoustic material in the problem, we see that there's a significant increase of noise reduction caused by the absorbing capability of that glass wool material. Okay, so with that, I will end my presentation and demonstration.